Okay, let's continue with chapter 4, pure bending. So these are the content of the chapter. So basically, pure bending, as I explained in earlier, so type of stress, we have normal stress and we have shear stress. Okay, so normal stress is formed due to first axial load, and then the second is because of bending moment. So axial load happens when you have, let's say, a sample like this, and then you apply load at both ends like this. So it will cause a normal stress because the force is actually perpendicular to the area. So bending moment, let's say you have a specimen like this, and then you apply force. So this will cause the specimen to bend like this. So this also will cause normal stress. However, the shear stress, let's say you apply, first is transverse load. Transverse load is not like this load. Okay, transverse load is, this is your specimen. So if axial load, you apply load like this. This is axial load because this is the area. But for transverse load, you apply load like this, which is parallel to the area. So this will break here. So this is transverse load. So this will cause shear stress and also torsion because you twist maybe at both ends. So it will cause shear stress. So basically, for bending moment, it is more likely that you are talking about normal stress. Okay, we are talking about normal stress. Okay, let's have a look at this picture. This Olympic Games, that this guy is actually lifting the bar, this bar, weight bar. Okay, at point C and D where his hand is holding the bar. So this point from C to D, we said experiencing pure bending. Okay, so because there is a load here equal to 32 Newton, and the distance from D to here is 300 millimeter or 0.3 meter. So the moment at point C and also at point D is equal to force times distance. So it is equal to 32 newtons times 0.3. So you will get 9.6 nanometer. Okay, point C and point D. So this is transverse load. So transverse load is the load where this is the area. So transverse load is where the load is parallel to the area. So it will break here because point B is connected to the wall. Okay, so this will break here. So the moment occurring is actually, the bending moment is occurring here. Bending deformation, this is the principle of a bending deformation. So this is the original dimension before deformation, before bending. Before bending, it is like this, straight, and then you give force, and then it will become like this. So the top part, so in the middle we have a neutral axis at the top. So this is the neutral axis. So the top part here on top of the neutral axis experience compression. The distance, the length will become decreasing, and this will experience tension. So this tension will experience, the length will be increasing, and then the compression, the length will be decreasing. Okay, for the principle, when beam, this is beam, is subjected to bending, so the member remains symmetric. So from this area, 1 and 2 is symmetry. 1 is equal to 2. Symmetry bends uniformly to form a circular arc. So when you bend, this actually form a circular arc. So, and this is the center. Okay, this is the center. So it will create a circular arc like this. Okay, length of top decreases, as I said, because it experiences a compression. So this will experience compression. So tops decreases and length of bottom increases because this experience tension. So the neutral axis in the middle, this is neutral axis, we call it neutral axis, must be parallel to the upper and lower surfaces for which the length does not change. So the length before bending and after bending for the neutral axis does not change. Stresses and strain are negative, in which that on top of the neutral axis, because it is compression, so the strain and stress, this is the strain and the stress is negative because it is compression. And then below this area to the bottom will experience tension, so it will cause positive value because it is tension. Strain due to bending. So what is strain? This is strain. Okay, we are talking about strain now. Okay, so consider a beam initially like this, and then after tension, after bending, it will become like this. So as I said, in the middle there is a neutral line. This is a neutral line. So in this case, the neutral line is this line. This is the neutral axis or the neutral line. So this is neutral. Okay, now we consider L. This is L. This line from here, from this point to this point. This is L. L prime, okay? So after bending, the L at this area will change to L prime. Okay, so L prime can be calculated using the equation rho minus y times theta. So it's like that you have a circular arc like this. This is the center. So you want to know what is the length. Let's say from this is, let's say this is point A, this is point B. So we call it S.
Just a moment. Go ahead.
So we call it S. So this is a center. Do you have theta? And then you have radius. So S is equal to R times theta. So similarly, length prime can be calculated using this equation, rho minus y times theta. So this is rho, which is the length of the radius from center to the L, from here to here. Okay, from here to here. And then y is actually the length from here to here. So this is actually y. So this length from here to here, this from here to here, from a C to J is equal to rho minus y. So that's why you get rho minus y times theta. Okay. So delta is the deformation. Deformation is equal to length prime minus length prime, L prime minus L. So the deformation, because initially this length and this length at the neutral is the same, but after bending this length has changed. So that's why we calculate the deformation. So length L prime is equal to this, which is you change to this, And then L can be calculated using this equation, rho times theta. Rho times theta is equal to L. So if you simplify, so you solve this problem, so it's equal to rho times theta minus y times theta minus rho times theta. So this can be cancelled with this, so finally you will only get minus y times theta, which is this one. So strain in x direction is equal to delta over L, as we have as we discussed before. This is the equation for strain. Strain is equal to length final minus length original over length original. So this can also be simplified into delta over L original. So this delta is equal this one, so same. So this delta is actually L prime